All right, pre-calc stars, I'm back. I'm not sure how necessary these two examples are, but I figured since I wrote them down earlier, they probably will help you guys out. So, but the first few examples kind of told you guys, hey, I need to factor the denominators to make sure that I'm not doing more work than necessary. Because I've seen students before who have just basically straight up said, I need a p minus 2, a p plus 4, and a p squared plus 2p minus 8. They've multiplied it out, and the expansion was a nightmare for everybody involved, especially them. They had to take all that time to work through it. If you factor this first, then you are privy to some very important information. P plus 4 times p minus 2 is p squared plus 2p minus 8. Which means this one needs a p minus 2. And this one needs a p plus 4. And once you do that, there's not a lot of legwork that goes beyond that. So 2p minus 4 over the same thing. One p plus 4. Identical denominators, so you can ditch them. And then I'm instantly going to just add these. So that's 4p. 1 minus 4 is negative 3. And then I'm going to subtract 1p from both sides and add 3. So 7 is equal to 3p, divide by 3, divide by 3. 7/3 is 2 1/3. Just make sure that it doesn't conflict with any of the domain issues. The domain issues are positive 2 and a negative 4. Those are the numbers that make 0 on the bottom. We don't want 0 on the bottom. This one's okay. All right, last example. All right, once again, if you get a little bit antsy about the whole finding a common denominator deal, don't just multiply everybody by the other denominators. Because something interesting is happening here. You can factor a 3 out of 3n plus 3. So divide by 3, divide by 3. Interesting. You can take out a 4 here. N minus 1, n plus 1. And then, of course, you see there's a 2 that goes into both of these. 2, 2n plus 1. Now from there we can find kind of dual common denominators. Like there's a common denominator of just the constants here. So it's basically like what's the least common multiple of 3, 4, and 2? It's 12. So you multiply that by 4, multiply that by 3, and multiply this by 6. Everybody's got a 12 out front now. Additionally, everybody's got to have an n plus 1 and an n minus 1. So this needs an n minus 1. So the top needs an n minus 1. This needs an n plus 1, as does the top. And this needs an n minus 1, top 2. So it's really messy right now. If you kind of got lost in that, just rewind the video, watch it again. The denominators are the same. They're all 12 n plus 1, n minus 1. Maybe just the order is reversed. Commutative property says order doesn't matter. All right, so this is the step where the denominators are now gone. I'm ditching them. So now we got 28n times n minus 1, subtracting 15 times n plus 1, and that's equal to 18n times n minus 1. Use the distributive property to make the parentheses disappear. Yeah, and at this point you can create a polynomial on the left-hand side by moving the 18n squared to the left. And the 18n also to the left. Doesn't matter who you add to, it's kind of like a running total with these n's. So it looks like you've got 18n squared. Negative 28 plus 18 is negative 10. Minus 15 is minus 25n. And then you got minus 15. Now I'm noticing something at this point. They all seem to have a factor of 5. Let's divide that out. And since it's a constant with no variable, I can just divide by the other side of the equation and get rid of it completely. I don't have to factor it out. All right, now, did this conveniently become a polynomial that's factorable? Here, over here now. Whoa, wobbly. The answer is yes. I mean, we're trying to multiply to get negative 6 and add up to give negative 5. So negative 6 plus 1. If you're thinking guess and check, 2n times n gives 2n squared. 3 times 1, I know this is 3 because that gives me my negative 6 plus 1n. And it equals 0. And there we go. Subtract 1. Divide by 2. Add 3. Double check to see if there's any domain issues in the original problem. Looks like the domain issues were just negative 1 and 1. But you know what? I've had students ask this question in the past. I think that's why I picked this problem. They see the 3 and they're like, wait, does that mean 3, 4, and 2 are domain issues? And the answer is no. Just having a constant on the bottom of a fraction doesn't suddenly mean that that number can't exist on the bottom, because it does exist. It exists right there. So sometimes people try to make up rules just because. Okay. By the way, if you ever want to check these, just to make sure you're doing it right, I mean, go to the original statement. Go to that original equation, plug in 3 for here, 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 and here, and see if the left-hand side actually matches up with the right-hand side. I think you'd be surprised at how quickly you can actually do it. It just seems like a task that's too heavy. How about I just show you how quickly it actually does move? Okay. So let's say I want to check these two answers. plug in a 3 here, so that's 21. Plug in a 3 here, that'd be 3 times 3, 9. 9 plus 3 is 12. And then a 3 here would be 12 minus 4, that'd be 8. Common denominator would be 24. Over here it'd be 9, 3 times 3, over 2 times 3, which is 6. 6 plus 2 is 8. This is 42. Minus 15 over 24. Okay, so this is 27. This is 27. Okay, check out. How long did that take me? Yeah, it might have taken me a minute. If you got a calculator, oh shoot, you didn't even see it. My apologies. This is happening way too often. All right, but bottom line, 3 works. Negative 1/2 also works. I'm gonna quit while I'm ahead. Hopefully this video was helpful, guys. And yeah, that's lesson 1.4, part 4.